Welcome to today's problem walkthrough. In this session, we will dive into LeetCode problem number 1555, titled Minimum Sum of 4-Digit Number After Splitting Digits. We'll explore how to split and rearrange digits strategically to achieve the minimum sum of two numbers. Let's get started. The problem is to determine the minimum possible sum of two integers that are formed by splitting and rearranging the digits of a given 4-digit number. For example, you're given a number, which is guaranteed to be a 4-digit integer, ranging between 1000 and 9999. The goal is to split the digits of this number into two groups, rearrange them to create two new integers, and calculate their sum. The challenge is to find the smallest possible sum that can be achieved through this process. The input to the problem is a single integer, number, and the output is also a single integer, representing the minimum sum. This means that the solution must not only split and rearrange the digits correctly but also ensure that the resulting sum is the smallest it can possibly be. Consider an example where the input number is 2932. First, we split the digits of number into individual components, 2, 9, 3, 2, then, we rearrange these digits into two groups, such as 2, 2, and 3, 9. From these groups, we form two integers, 22 and 39. When we add these two numbers together, their sum is 22 plus 30, which equals 52. This is the minimum sum that can be achieved by splitting and rearranging the digits of 2932 in this way. This process demonstrates how careful grouping and rearrangement can lead to the smallest possible result. Now let's look at another example where the input number is 4009. Here, the digits of number are split into 4, 0, 0, 9. After rearranging, we can form two groups, 0, 4, and 0, 9. These groups lead to the numbers 4 and 9. When we calculate their sum, we get 4 plus 9, which equals 13. This is the smallest possible sum for this input. Notice how the presence of zeros requires special attention during the rearrangement process to ensure the result is minimized. Proper handling of zeros is critical to achieving the correct outcome. Finally, let's discuss some additional cases to consider. If the digits of the number are already sorted, such as 1234, the solution must still split them optimally to achieve the minimum sum. For example, splitting as 1, 2, and 3, 4 would yield 12 and 34, resulting in a sum of 46. Similarly, for a reverse-sorted number like 9876, the solution must manage the digits carefully even though they are in descending order. The process should always prioritize balanced splitting and rearrangement to minimize the sum, regardless of the initial order of the digits. These scenarios highlight how the problem requires attention to detail in all possible configurations of the input number. To solve this problem, we aim to minimize the sum of two numbers formed by splitting and rearranging the digits of a given 4-digit integer. One approach to consider is the brute force method. The idea here is to generate every possible way to split the 4 digits into two groups. For each grouping, we rearrange the digits to form two numbers, calculate their sum, and track the minimum sum across all combinations. While this approach is intuitive and ensures we explore every possibility, it has significant drawbacks. Specifically, the number of groupings grows exponentially with the number of digits, even though we are limited to 4 digits in this problem. This makes the brute force solution computationally expensive and inefficient, especially when compared to more optimized methods. A much better approach is the greedy method, which is both more efficient and easier to implement. The key insight here is that the minimum sum is achieved when the two resulting numbers are as balanced as possible and their digits are minimized. To achieve this, we can simply sort the digits of the input number in ascending order. Once sorted, we can form the two numbers by grouping the smallest digits together. Specifically, the first and third smallest digits form one number, and the second and fourth smallest digits form the other. This ensures that each number is as small as possible, leading to the minimum total sum. The steps are straightforward: extract the digits, sort them, pair the digits as described, and return the sum. With a fixed input size of 4 digits, the computational complexity of this approach is constant, making it extremely efficient. Given the options, the greedy approach stands out as the most efficient and elegant solution to this problem. The fundamental observation is that sorting the digits allows us to directly pair the smallest digits together, ensuring that the resulting numbers are minimized and balanced. This method avoids the inefficiency of generating all possible groupings, as seen in the brute force approach. Its efficiency is unbeatable since the input size is fixed, all operations, including sorting and forming the numbers, run in constant time. Additionally, the simplicity of the logic makes it easy to understand and implement. While the greedy approach does assume that pairing the smallest digits together always yields the optimal result, this assumption holds true for the given problem constraints. In contrast, the brute force method, though comprehensive, is impractical due to its exponential nature. Overall, the greedy approach is the best choice, balancing efficiency, correctness, and simplicity. To solve this problem, the goal is to take a 4-digit number, split its digits into two integers, and rearrange them so that the sum of these two integers is minimized. The first step in achieving this is to extract the individual digits of the number. For example, if the input number is 2938, we break it down into its digits, 2, 9, 3, and 8, forming the list 2, 9, 3, 8. This step is essential because it allows us to manipulate and reorganize the digits freely. Next, we sort these digits in ascending order. Sorting ensures that the smallest digits are prioritized, which is crucial for minimizing the sum. So, from the original list, 2, 9, 3, 8, sorting it gives us 2, 3, 8, 9. By organizing the numbers this way, we set ourselves up for optimal distribution in the subsequent steps. Now that the digits are sorted, we can proceed to form two new numbers. To do this, we distribute the sorted digits into two groups in an alternating pattern. Specifically, we take the digits at index 0 and 2 to form the first number, and the digits at index 1 and 3 to form the second number. For example, with the sorted list 2, 3, 8, 9, the first number is formed by combining 2 and 8, resulting in 28, while the second number is formed by combining 3 and 9, resulting in 39. This alternating distribution helps ensure that the two numbers are as close in magnitude as possible, which minimizes their total sum. Once we have the two numbers, we simply add them together. In this case, 28 plus 39 equals 67. Finally, the computed result, 67, is returned as the output. There are a few key insights that make this approach effective. First, sorting the digits plays a critical role. By arranging the digits in ascending order, we ensure that the smallest values are used first, which directly contributes to minimizing the final sum. Second, the method of alternating the digits between the two numbers ensures that their magnitudes remain balanced. This prevents one number from becoming disproportionately large compared to the other, which could lead to a higher sum. Lastly, the algorithm employs a greedy strategy, always selecting the smallest available digits for the most significant positions in the two numbers. This combination of sorting and alternating distribution ensures an optimal solution. To implement this algorithm, we rely on two key data structures. First, we use a list to store the digits of the number after extraction. Lists are particularly useful here because they allow us to easily sort and access specific elements as needed. Second, we use integer variables to form the two resulting numbers and compute their sum. Integer operations are both efficient and directly aligned with the requirements of this problem, as we're ultimately working with simple numerical calculations. These data structures together provide the foundation for an efficient and straightforward implementation of the solution. Analyzing the algorithm's complexity, we find that it is highly efficient. Extracting the digits from the input number is an O(1) operation because the number of digits is fixed at 4. Sorting these digits involves O for log4, which simplifies to O(1) since the input size is constant. Finally, forming the two numbers and calculating their sum are also O(1) operations. Combining these, the overall time complexity of the algorithm is O(1). Similarly, the space complexity is O(1) as well, because we only use a fixed-size list to store the digits and a few integer variables to compute the result. This makes the solution both time and space efficient. Several edge cases demonstrate the robustness of this approach. First, if all the digits are the same, such as in the number 1111, the algorithm still works because sorting and alternation naturally result in evenly distributed numbers. For example, 11 plus 11 equals 22. Next, if the digits are already sorted, such as in 1234, the algorithm simply keeps the order intact, resulting in a minimal sum of 13 plus 24, which equals 37. Lastly, if the digits are in descending order, like 9876, sorting reverses their order to ensure optimal allocation. After forming the numbers, we get 68 plus 79, which equals 147. These examples highlight how the algorithm handles different scenarios effectively while maintaining its correctness. The provided solution is designed to find the minimum sum of two numbers formed by splitting the digits of a given four-digit number. Here's the explanation of the code. 1. Extract digits from the number. The first step is to convert the input number into its individual digits. By converting the number to a string and iterating through it, we can extract each digit as an integer. For example, if number equals 2938, then digits equals 2, 9, 3, 8. 2. Sort the digits. To ensure that we can form the smallest possible numbers, we sort the digits in ascending order. After sorting, the digits 42938 become 2, 3, 8, 9. 3. Form two numbers to minimize the sum. Once the digits are sorted, we can form two numbers by pairing the smallest and next smallest digits together. The first number is formed by combining the smallest and third smallest digits, digits 0 and digits 2, and the second number is formed by combining the second smallest and largest digits, digits 1 and digits 3. For example, after sorting 2938, the two numbers formed are number 1 is equal to 2 times 10 plus 8 equals 28 and number 2 is equal to 3 times 10 plus 9 equals 39. 4. Return their sum. Finally, the sum of the two numbers is returned. For the example 2938, the sum is 28 plus 39 equals 67. This approach guarantees the smallest sum because sorting ensures that the smallest digits contribute the most to the tens place, minimizing the overall value of the two numbers. The solution has a time complexity of 1, since the number of digits is fixed at 4, and sorting a list of 4 elements is a constant time operation. The space complexity is also 1, as the algorithm uses a fixed amount of additional space regardless of input size. In summary, the solution is efficient and directly addresses the problem requirements, ensuring the minimum sum is achieved by leveraging digit sorting and careful pairing. This is the Java implementation of LeetCode problem number 1555, minimum sum of four-digit number after splitting digits. It mirrors the logic of the Python solution by extracting the digits, sorting them in ascending order, and constructing two numbers to achieve the minimum sum. Key differences include the use of Java's primitive arrays, arrays.sort for sorting, and type declarations. The code follows Java conventions and is structured within a class definition. To solve this problem, we start with the example number 2931. The first step is to break this number into its individual digits. By converting the number to a string and using a list comprehension, we extract the digits as 2, 9, 3, 1. Once we have the digits, the next step is to sort them in ascending order. Sorting ensures that the smallest digits are prioritized for forming the numbers, which helps minimize the final sum. After sorting, the digits become 1, 2, 3, 9. Now, to construct the two numbers, we pair the smallest digits together, forming one number with the smallest and third smallest digits, and the other with the second smallest and largest digits. Using the formula digits 0, 10 plus digits 2, and digits 1, 10 plus digits 3, we calculate number 1 as 13 and number 2 as 29. Finally, we return the sum of these two numbers. Adding 13 and 29 gives a result of 42, which is the minimum possible sum for this example. Now, let's look at the next example, where the number is 4009. The process begins the same way. We extract the digits of the number, resulting in 4009. After extracting the digits, the next step is to sort them in ascending order. Sorting the digits gives 0049. With the digits sorted, we create two numbers by pairing the smallest digits first. Using the same formulas as before, digits 0, 10 plus digits 2, and digits 1, 10 plus digits 3, we calculate number 1 as 4 and number 2 as 9. Finally, we add these two numbers together. The sum is 4 plus 9, which equals 13. This is the minimum possible sum for the number 4009. Let's now consider the final example, where the number is 1234. The digits of this number are extracted as 1, 2, 3, 4. Since the digits are already in ascending order, there's no need to sort them. Using the same approach as before, we form two numbers by combining the smallest digits first. From the sorted digits, we calculate number 1 is 1 by 10 plus 3, which equals 13, and number 2 is 2 by 10 plus 4, which equals 24. Adding these two numbers gives a sum of 13 plus 24, which equals 37. This is the minimum sum for the number 1234. To analyze the time complexity of our solution to problem number 1555, let's break it down into its main operational steps. First, we extract the digits from the input number. This involves converting the integer into a string, which takes k time, where k is the number of digits. Since the input is always a 4-digit number, k equals 4, so this operation is performed in constant time, 4. After converting the number to a string, we use list comprehension to transform each character back into an integer. This step also takes k, or 4, as we are iterating over a fixed number of digits. Next, we sort the list of digits. Sorting a fixed-length list of 4 elements has a time complexity of for log 4, which simplifies to 1, because the input size is constant. Finally, we form two numbers by combining the digits using arithmetic operations like addition and multiplication. These operations are constant time, 1. Returning the sum of the two numbers is a single operation, which completes in 1 time. Adding up the time complexities of all these steps, we see that the entire algorithm runs in constant time, or 1. Now, let's turn to the space complexity. The input number is stored as an integer, which requires 1 space. For intermediate storage, we use a list to hold the 4 digits of the number. Since the number of digits is fixed at 4, this requires 4 space, which simplifies to 1. Additionally, we use two variables, number 1 and number 2, to store the two resulting numbers. These are integers and also require 1 space each. No additional data structures are used in this solution, and all the operations are performed using a constant amount of memory. This means the overall space complexity is 1. To compare this with a brute force approach, we can see the clear advantages of the optimized solution. A brute force method would involve generating all possible ways to split the 4 digits into two 2-digit numbers. Generating all permutations of the digits would take 4, which equals 24 permutations, and calculating the sum for each pair would take 1 time per operation. While the brute force approach technically has a time complexity of 1, for this specific problem due to the fixed input size, it is less efficient in practice because of the larger constant factor associated with generating permutations and checking sums. In conclusion, the optimized solution is both simple and highly efficient, achieving time and space complexities of 1. By directly sorting the digits and using basic arithmetic operations, it avoids the computational overhead of generating and evaluating unnecessary permutations. This approach ensures that the smallest possible sums can be calculated quickly and with minimal resource usage, making it a clear improvement over brute force methods both in terms of elegance and performance. When solving this problem, there are a few common mistakes to watch out for. First, not sorting the digits before splitting them is a frequent error. Sorting ensures that the smaller digits are placed in lower place values, which minimizes the sum of the two numbers. For example, with the digits 29-31, if you split it directly into 29 and 31 without sorting, the sum is higher than if you first sort the digits to 12-39 and split them into 12 and 39. Sorting is essential because it guarantees the most efficient distribution of digits. Another mistake is using an incorrect splitting strategy. Some might assume that you can only split into two equal-sized groups of 2 digits each, but this isn't a requirement. The problem allows any valid pairing of digits, so failing to explore other combinations could lead to suboptimal results. Finally, overcomplicating the solution is another pitfall. Some people resort to nested loops or recursion to check all permutations of digits, but this is unnecessary. Sorting the digits and applying a greedy approach is both simpler and faster, avoiding the inefficiency of higher time complexity methods like n superscript 2, or worse. Another issue to be mindful of is handling leading zeros correctly. If the digits include 0, and you generate numbers with leading zeros, like splitting 0, 1, 2, 3, into 0, 1 and 23, it can create logical errors. Leading zeros should be avoided because they don't contribute valid numeric values. Additionally, edge cases require special attention. For instance, when all digits are the same, like 11, 11, or when there are repetitive patterns, such as 12, 12, it's easy to miss how the solution behaves in these scenarios. Overlooking these edge cases can result in solutions that fail under certain conditions. Ensuring your implementation accounts for these situations is key to building a robust solution. Now let's focus on strategies that can impress in interviews. A key insight for this problem is that sorting the digits is the most efficient way to minimize the sum. By sorting, you ensure smaller digits are allocated to lower place values, which is crucial for achieving the smallest total. A greedy approach works well here. After sorting, alternate the digits between two numbers, assign the smallest digit to one number, the next smallest to the other, and so on. This guarantees an optimal distribution. When explaining your solution in an interview, make sure to clearly articulate why sorting is necessary and how this greedy assignment minimizes the sum. Clarity in your thought process and logical reasoning can make a strong impression. Additionally, be prepared to discuss optimization. Sorting has a time complexity of n log n, which is significantly better than a brute force approach that uses permutations and has factorial time complexity. Highlighting these points demonstrates both efficiency and a deep understanding of the problem. To deepen your understanding, it's helpful to explore related problems on LeetCode. For example, in LeetCode 31, next permutation, you rearrange digits to meet a specific condition, which is similar to the process of optimizing digit distribution here. LeetCode 56, merge intervals, introduces sorting-based strategies for merging or splitting data, which also requires a systematic approach. LeetCode 1015, smallest integer divisible by k, involves digit manipulation and number formation, tying into the logic of rearranging digits efficiently. Lastly, LeetCode 216, combination sum 3, focuses on generating subsets and combinations, which relates to the idea of splitting a set of digits into optimal groups. These problems reinforce key techniques like sorting, greedy algorithms, and subset generation, all of which are applicable in this context. Finally, let's explore alternative approaches. One method is brute force, where you generate all permutations of the digits and evaluate every possible split. While this guarantees you'll find the optimal solution, it's highly inefficient, with a time complexity of n. For larger inputs, this approach quickly becomes impractical. A better option is the sorting and greedy splitting strategy. Here, you sort the digits and then alternate their assignment to two numbers. This approach is efficient, with a time complexity of n log n, though it might require extra space for sorting. Another intriguing option is mathematical optimization, where you directly compute the results based on analytical patterns of digit distribution. This eliminates the need for explicit sorting, reducing runtime further. However, deriving and implementing such a formula can be complex and error-prone. Each approach has its trade-offs, so choose the one that best balances efficiency and simplicity for the given context. Great job! We've successfully solved the problem and reviewed the optimal approach. Remember, sorting and breaking down the problem were key to our solution. Thanks for watching, and I hope to see you in the next session. Don't forget to like and subscribe for more problem-solving guides. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!